The strong force. The nucleus of an atom contains positively charged protons that will be repelling each other. We can calculate the strength of the repulsion between neighbouring protons. If we assume a proton has a radius of 1 times 10 to the minus 15 metres, a femtometre, the centres of two neighbouring protons will be a distance of 2 femtometres apart. Using Coulomb's law, which is given here, putting in the values, the charge on the proton is 1.6 times 10 to the minus 19 coulombs, and the separation we've said is 2 times 10 to the minus 15 metres. This gives a force of repulsion of a massive 57.5 newtons. This is a huge force on such a tiny particle. There will, of course, be an attractive force due to gravity, given by Newton's universal law of gravitation. Putting in the values, with the mass of the proton here, gives an attractive force, shown by the minus sign, of 4.7 times 10 to the minus 35 newtons. This is against the repulsive force of 57.5 newtons. Clearly, gravity cannot be the force that holds the nucleus together. A much stronger but very short-range force, called the strong force, is what holds the nucleus together. I've tried to represent the strong force and electrostatic repulsion in these diagrams. A proton, being positively charged, has electrostatic repulsion acting on it, shown by the blue shading here, and it also experiences the strong force, shown by this pink shading. The neutron experiences the strong force, shown by the pink shading, but is neutral, so has no electrostatic repulsion, hence no blue shadow. So two protons this far apart would be repelling each other. Their blue clouds are in contact. They would not feel the strong attraction. Their pink clouds are not in contact. These two protons will feel the strong force. The pink clouds are in contact. They'll also feel electrostatic repulsion. This combination of two protons is not stable. However, if we add a neutron here, this will add strong force without adding any electrostatic repulsion, and this gives us the smallest stable multinucleon nucleus, helium-3. Here we've got a carbon-12 nucleus. Let's consider this proton. It will feel electrostatic repulsion from all the protons in the nucleus. Even the one over here will have its blue cloud crossing over with the blue cloud from this one. They will be repelling each other. However, this proton is attracted with the strong force to its three neighbours. It won't feel the strong force from any other of the nucleons in the nucleus. They're just too far away. The strong force is certainly strong enough to hold a carbon-12 nucleus together. However, as we get to larger nuclei, we get an increasingly large number of neutrons to protons in the nucleus. This is because the neutrons add strong force without adding electrostatic repulsion. This makes the nuclei more stable. The strong force must be repulsive at very small distances, otherwise the nucleons would just collapse in on themselves. This graph shows how the strong force varies with separation. You'll see at very short distances the force is positive, showing it to be repulsive. Look at the values, 20,000 newtons. As we get further away, at about half a femtometre, the force becomes 0 before becoming a negative or attractive force, going down to around about 20,000 newtons of attraction. It rapidly falls away, becoming effectively 0 at around 3 times 10 to the minus 15 metres.